Hi, everyone, and welcome back. We're going to talk today about three different topics, which are a bit distinct, but it's also a good order to sort of have one lead into the other. We're going to talk about fully connected networks, now that we've gone through the exercise of automatic differentiation. Then we're going to talk about basically how we actually start making these networks in practice, work in practice. So we're going to talk in particular about optimization of these networks and then initialization. All right, so let's jump right in. And first, start talking about fully connected networks. This is actually going to be, in some sense, just kind of a rehashing of the same material we covered in lecture 3, so three lectures ago now. But the basic idea here is that now that we've covered automatic differentiation, we can actually be much simpler in our definition of fully connected networks. And we can also be a bit more flexible too. We can add a few more elements to them that are kind of common in practice. So in particular, we're going to define a L-layer fully connected network, also called a multi-layer perceptron or MLP, in the following way. We're going to say that Zi, the I+1th activation or just layer in the network, is equal to some nonlinear function sigma of a linear function of the previous layer plus a bias term bi. And now in this case, we're actually going to be explicit about including this bias term bi, which we didn't include before, mainly because when we went through the exercise of manually driving backprop, it was just one more term to deal with. But now that we've sort of simplified this using automatic differentiation, or at least how we do these things, we're going to include it because it's pretty standard. We're going to define the output of the network as just the L+1th layer. So we repeat this iteration at first L times, and then the output is just the last value of that iteration. And we also define the first layer just being equal to x, the input to the network. Now the parameters of our network here are W1 through L and B1 through L. That makes up our set of all the parameters theta. And sigma I is some nonlinearity. So that's the nonlinear activation function, like a ReLU or a sigmoid. We're typically going to use ReLUs for most of the examples in this course, so at least for the first bit. And then usually it's also the case, though, this sigma I can vary depending on I here. And usually it's the case that we choose the last layer to just be the last nonlinearity to be a linear function, so that our lodges essentially are a linear function of the last layer. All right, so this is going to be our network. And just to find a few more things here, I want to mention that if we look at the sizes of these things, Zi, if we say, we're not going to dwell too much on this because the reality is, for the most case, you don't really need to worry about these things because you can just define them once and then that sort of works. But let's give names to all these things here. Let's say that Zi would be a vector in Ni. So Ni would be the size of the ith layer. Well, in that case, Wi then would be a matrix. Well, Wi transpose has to map Ni to Ni+1. So Wi would be Ni by Ni+1. And of course, Bi would also then be vectors in Ni+1. It's important to note here that Bi is a vector in Ni+1 because we're adding it to sort of the output of our linear transformation, and so it has to be the size of the next layer. And the nice thing is that now that we've defined automatic differentiation, we are now done. So this is a full, complete definition now of a fully connected network. And unlike before, we don't have to worry about deriving the backprop equations for this, of finding gradients of all these things when it's connected to as part of a larger network. Because now we can just implement these operations in the forward pass of a network and let our automatic differentiation tool give us a way of automatically computing the gradients. And that's an amazingly powerful thing, right? And it sort of shows the power of automatic differentiation, is that now we are done with our layer definition. Almost, not quite, because there is one little issue that I want to mention here, which seems like a minor point, but which you will actually end up spending a lot of time on when you implement some of your networks. You probably already started to encounter, if you've encountered homework 1 already on unbiased differentiation, you will encounter things relating to the size of these various operations, especially when, and vectors matrices here, especially when you use the matrix form of these expressions. So let's talk about the matrix form of these expressions. The most obvious thing here to do is say, well, we have our matrix form as before. Remember, we have our terms zi here. So zi is going to be like a stacking of all the z's, right? So we'd have, like, in the first row, it would have z1 transpose. I guess it would be zi1 transpose. In the second row, it would have z2 I transpose, etc. Sort of the list of all our activations for that layer in the rows. And we have this sort of now very simple matrix form that we saw before, right? So we're going to just apply these things in matrix form, and this is now because these things are already transposed here, you actually don't include the transpose and you include wi after it, but this is all the same as in our original fully connected networks. The difference here, though, comes in the bias term here. So remember, bi is a vector in Rn plus 1. Sorry, Ri. And I plus 1. And what this means is, if we didn't write this, so if we sort of cross this out for a moment and just wrote this in terms of bi, right? So sort of copying the notation from the previous slide. This really wouldn't work, right? Because this matrix here would be it would be m by ni plus 1. And that's a matrix, and you can't add to it a vector, right? These sizes don't sort of compute here. So what we need to do linear algebra-wise is adjust this slightly. And this is actually exactly the operation we're going to have here. The operation is going to be 1 times bi, where here 1 signifies the vector of all 1s, which in this case would be a m by 1 vector of all 1s. And then we would transpose bi, so that bi transpose here would be a 1 by ni plus 1 matrix. Sorry, matrix, or essentially a row vector of dimension ni plus 1. And their product then would be a m by ni plus 1 matrix. This product then is an m by ni plus 1 matrix, where each row of that matrix just includes basically a copy of bi, right? So basically this matrix here is just equal to a matrix that has bi transpose in the first row and also bi transpose in the second row, all the way down to m copies of this. Right? And that's kind of the linear algebra way we form these things. We have to do that in linear algebra, to write this sort of precisely, in order for these matrices to actually make sense, or these operations to make sense as matrix operations. Now, in practice, though, you don't want to actually do this. You don't want to form a m, or at least explicitly form a m by 1-dimensional row vector, multiply it as a matrix multiply with transpose version of your bias and all this kind of stuff. Because in practice, you actually don't form these matrices. You don't want to do that because essentially it just wastes space. We'll actually talk a lot about space and memory kind of waste later on, because there are some cases where you want to kind of form these on the fly for more efficient operations. But here, let's just say that, if we're talking just about kind of memory, we wouldn't want to form this matrix, right? This matrix that just contains a bunch of copies of the same thing. And so what we're going to do instead is talk about broadcasting. Broadcasting is a topic that you will deal with a lot in, you'll deal with it starting in homework 1, when you actually implement the automatic differentiation through broadcasting operators, which actually is quite subtle and takes some struggling through, and you will struggle through it a bit in your first homework. But the basic idea is that instead of explicitly copying this vector many times, we use this technique called matrix broadcasting. And matrix broadcasting is you may have seen it already if you've used libraries like NumPy before. NumPy has sort of a very advanced but confusing set of matrix broadcasting routines that can be quite confusing if you haven't seen them before. But the basic idea is broadcasting treats matrices that have singleton dimensions as matrices that kind of automatically expand their singleton dimension to repeat multiple times such that they sort of match the sizes of other matrices. And NumPy includes sort of very, as I said, sort of very involved broadcasting rules. But in Needle, the framework you'll be writing, we're actually going to use a much more explicit form of broadcasting. So for example, in Needle, if you wanted to take a ni plus 1 dimensional vector, so if you want to take, say, this bi vector here, and treat it as a essentially m by n dimensional matrix, you would need to do the following. You would call something like b. You'd first have to explicitly reshape it, because b starts out as just an ni plus 1 one-dimensional tensor, essentially, and or 1D tensor with ni plus 1 dimensions. And so you want to just call something like reshape to first pass a new size to it, which would be in this case 1 by, I'm gonna sort of mix math and code here, but that's sort of the variable for ni plus 1. So you have to call it to sort of first reshape it to the proper size. And of course, this is valid because this doesn't change the number of elements in it, right? It just sort of adds one more dimension to our tensor. And then you would need to broadcast it to some other shape. So you would have to call the function broadcast to m, it's a size here, so it would be in a tuple of m and ni plus 1. And something like that, right? Now, this is not an implementation lecture, so I'm just going to say this here. But these are the sort of operations, I'm going to say this briefly, but these are the sort of operations you want to do to resize this properly. And I'll just mention it because this is something you will have to do for the first assignments. But more importantly, you're going to have to think about how these reshape operations and these broadcast operations actually are implemented in automatic differentiation sense, because that actually is not that trivial. You have to sort of think about what's, if you have an operation that broadcasts, how do I compute the adjoints of this, right? And it's somewhat tricky, but if you think about it for a while, you'll be able to figure it out, and you will in fact implement this in your first homework. So you will work this in your first homework. But that's just a quick note, because these seem like kind of details, but they actually are very important from the sense of implementation, because you need to know what you are copying and what you are not copying. And this is sort of the basics of how we do that in linear algebra, at least when we implement them in a library like NumPy or like Needle. All right, so now that we have these fully connected networks, we have a bunch of questions we can kind of ask about these things. And to be honest, the next several lectures are going to be about how we both kind of mathematically train networks like this to solve some task, but then also how we implement them. So this lecture is going to kind of cover things like how we can optimize the parameters for networks like this. Actually, it's going to be about optimization in general, but this will be applied now to the problem of optimizing these sorts of problems. And we're also going to talk a bunch about sort of the other details, like how do you actually implement kind of a Python library that does these things all in a very nice and modular fashion? How do you ensure that this, what layers or what aspects can you add to this library to ensure that optimization, initialization, all these things kind of play nicely together? Okay? And then these are going to be a bunch of sort of, in some sense, very problem-specific answers, but by going through all of these points in the next several lectures, you'll be able to get a sense of sort of how you accomplish these things. All right, let's jump right in then to optimization. Remember, the basic problem that we have of a network, no matter what, and I'll just repeat this here because you've seen it before, but I'll sort of write it again briefly. This is the core optimization problem. You'll see it actually in several slides again. But our core optimization problem, remember, is that we want to minimize over our parameters theta, the average, minimize, the average of our loss of our hypothesis on this example and the output. Right? That is our goal. And for the purposes of this section, though, I'm going to call this whole thing here just f of theta, because it's just some function. The function we're trying to optimize over in terms of the optimization, it's just some function of our parameters. And we want to find the parameters that minimize this value. In this case, the parameters, for example, in the case of a fully connected network, the parameters would be, as I said, W1 through L and B1 through L. But really what's important here is that we're just trying to optimize some function. Right? And so what we're going to do now is we're actually going to take a deeper look at some of the optimization methods that are used in practice for a lot of deep learning training, essentially. And before I said that, oh, we use gradient descent or stochastic gradient descent, that's not entirely true. There actually are a bunch of modifications of SGD and gradient descent that we use very commonly in deep learning. So we're going to cover these in this next section now. Let's first start off by just recapping gradient descent. So remember, our gradient descent algorithm was an algorithm that took our current values of the parameters and just set them equal to those values minus some small multiple of this gradient term. Where before we computed this gradient term kind of by hand, but now this gradient term here, the beauty is that we can get it kind of done automatically for us through automatic differentiation. Now, before when I wrote things, I wrote them as our parameters theta were equal to theta minus some multiple of the gradient, right? This is how I wrote things before. But all I want to say here is that for this section, I'm going to be a bit more explicit, and I'm going to have explicit subscripts that indicate which iteration of our algorithm we're in. So T here is going to be the iteration number of our algorithm. And the reason we do that is just easier. This is sort of this would be like the implementation view of these things. This would be sort of how we implement in code or sort of algorithmically the gradient descent algorithm. But mathematically, it's nice to think about these in terms of sort of a progression of these parameters over time. Of course, you don't want to store all the parameters, right? You don't want to store all the parameters theta t plus 1, all your parameters from your first iteration of gradient descent to the end. You want to overwrite them, of course. But mathematically, it's nice to think about these things being kind of evolutions over time. I also want to sort of remind everyone about this weird gradient notation where this theta here indicates which parameter we're differentiating with respect to. We don't really need that here because there's only one parameter of our function f, but it indicates sort of which parameter we're differentiating with respect to. And this parameter here is the value that we are evaluating the gradient at. So this notation also makes more clear kind of what this gradient really means. This one I've always found a bit confusing, again, despite the fact that we have to use it because it's what people use. And remember, and here, of course, alpha was our step size. So this was the gradient descent algorithm we covered in a few lectures ago. And it's sort of the basis for, in some sense, all optimization. And what it does, remember, the gradient points in the direction of steepest increase of the function. So subtracting off the gradient here actually decreases our function in the steepest direction. And for a small enough step size, this will then cause a decrease in our function under various assumptions. All right, so that is our sort of basic starting point for optimization. That's the same as you've seen before. But now let's sort of take a few more looks into this in a specific case, because we're going to use this case when we talk about other methods, other optimization methods instead. So I'm going to actually consider a very simple quadratic function here that we're optimizing. So I'm going to consider here theta, in this case, just to actually be a two-dimensional vector, just so I can easily visualize these things. Where in these plots here, for example, when I show this plot like the ones you have here, I'm going to show this plot in terms of the evolution of theta. So the axes of this plot are theta 1 and theta 2. In other words, I'm showing the actual parameters. Oops, sorry, I should say that this is really in R2 or n equals 2, I guess. That's right, so it's written here too. This function now is a quadratic function is a function that has a quadratic term in p, and so this is the inner product of theta with a, in this case, p would be a 2 by 2 matrix, and q would be a 2-dimensional vector, so that when you take all these products here, you get a scalar output. And what these plots show here is these plots show the evolution of our parameters and the evolution of our function for, in this case, 2 different step sizes. So in the case of the step size alpha equals 0.35, we get sort of our function, our parameter values are kind of bouncing back and forth, right? So they start over here, we take a gradient step, it winds up here, then a gradient step here, etc., until we sort of reach the optimum of this function. Again, this function, what I'm showing here are sort of these circles here, or ellipses here rather, are the level sets of the function, so that they are points of constant value of the function. So the function kind of is curving out up from these points. And this shows the evolution of the parameters here. They kind of bounce around in space like this over the iterations of gradient descent. So this one here would be theta 1, this would be theta 2, theta 3, etc. And then this function here shows the evolution of our objective f theta. So what's the actual value of f theta at the different iterations? And that decreases as you would expect, right? So we're getting closer and closer to the optimum as we go here. But essentially, this point here kind of corresponds to like this point in the graph. And what I'm showing here is this for 2 different values of alpha. So what we see is with a larger value of alpha, you converge actually fairly quickly, but then you also kind of bounce around a bit in parameter space. Whereas if I take a smaller alpha equals 0.1, I converge more slowly, but I don't bounce around as much in parameter space. And these are actually the kind of trade-offs we talked about last time when it came to gradient descent. We need to kind of decide between, do we want to try to converge quickly? Do we want to try to not have our parameters change too much? How can we trade off, the different dimensions of optimization, these sorts of things? And this is all very hard to do kind of a priori, right? Because if you didn't know what this function looked like, and it wasn't just a 2D function, but an n-dimensional function, how would you know how to pick your step size, right? You probably have to just try out different things and see how fast they converge, see what caused divergence, this kind of stuff. And so in some sense, what the rest of the section is going to be about, and the rest of what a lot of optimization in deep learning deals with, is how we create updates that are able to more quickly reach low points or good points of our objective value without too much effort in tuning step sizes or maybe different step sizes and these sorts of things. This is really what a lot of practical optimization is about. So what we're going to do now is cover several alternative methods for optimizing this function, which may have different rates of convergence or different sort of, I guess, sort of different behavior of convergence. We're going to focus for the most part, at least for the first part, on this simple function here, which is in some sense quite misleading, because this is a simple, in this case, convex quadratic function. And the behaviors you see here are not always indicative of the behaviors you get for, I would say, real deep learning optimization. But it's nonetheless kind of instructive to think about how these algorithms would work on these simple objectives. But of course, the real proof is, in their operation, is how well they will work in sort of real deep learning and the optimization of real deep learning networks. So the first method that we're going to talk about as an alternative method for optimization is Newton's method. Now, Newton's method is kind of the classical second optimization method you typically see if you take an optimization course. So, you first learn about, well, maybe you first learn about like least squares, but then when you learn about iterative optimization, you typically learn about gradient descent, then you learn about Newton's method. And so because of that, I do want to highlight what Newton's method is here. But before I even highlight it, I will emphasize this on the next slide too. But before I even write it here, I want to emphasize that this is not very heavily used in deep learning. And I'll get to the reasons in a second, but Newton's method, despite being kind of, in many cases, the right approach to traditional optimization, it really does form the backbone for a lot of classical methods in convex optimization. It's not that heavily used in deep learning for reasons we'll discuss in a second. But let me just jump right in then and talk about what Newton's method is. So Newton's method is another kind of update, and I'll write it out. I'll just write it here. It's also written out in normal typing and in normal typesetting in the slides. But I'm going to write it here in the slides you can download. But I'm going to write it here just to sort of repeat these things and go slowly enough. The idea of Newton's method is we're going to do a similar update to gradient descent. So we're going to have our parameters minus some essentially some scaling of the gradient. So we're going to have our gradient term here, as we did before. But we're going to scale the gradient, and we're actually also going to have a step size, as we did before. But we're going to scale the gradient by a matrix. We're going to apply a matrix to this gradient before we take a step in it, which is going to, in some sense, give us the right direction for at least functions like the one you saw above, which are quadratic functions. So actually, maybe to motivate this, I'm going to go back to this previous slide for a second and motivate the fact that gradient descent, it seems like it's kind of taking a lot of time to do something very simple here, right? We sort of know in this function that the optimum is right here. So if we're starting over here, the fact that this function has sort of different magnitudes in different directions, this causes the gradient to kind of not be very aligned with the proper direction to the optimum. And it turns out for quadratic functions, or really for convex functions in general, when they're approximated by a quadratic, you can directly correct for this using what's called the Hessian, or which is essentially a set of second-order derivatives of the function. Okay, so let me just write out what I mean by that. What we are going to do in Newton's method is we are going to scale this gradient by a matrix, which I'm going to write like this. I'm going to write it as kind of looking like the gradient, but a little squared sign here. Of theta t. Oops, this is going to be theta t. This Hessian matrix here, and I'm going to invert it. And just without getting into too much details here, the Hessian matrix is sort of like a second derivative analog for multivariate vector input scalar output functions. So just like the gradient was the multivariate analog of the derivative, the Hessian is the multivariate analog of the second derivative. And in particular, the Hessian is defined as a matrix, or the Hessian, I should say something like this, for f mapping between Rn and R, so a scalar valued function. It's important this function takes vector inputs and produces scalar outputs. The Hessian is defined as a matrix of sort of all possible second derivatives of this function. All right, so it would be equal to a matrix of, first of all, the derivative of theta with respect to theta 1. Actually, in this case, it would be theta 1. And then the derivative with respect to the next column would be the derivative, second derivative of f theta with respect to theta 1, theta 2. Sorry, this actually would be, square should be over here. Then sort of etc. So this next one would be, all the way up to the derivative of f theta with respect to theta 1 and theta n, and similarly down here would be the second derivative of f theta with respect to theta 1, theta n. I'll still write it as theta n, theta 1, but of course that's the same as this thing. All right, so I'm running this quickly, and actually, I don't even have this formula on the slides. You can go back and kind of, or rather, you can go to sort of any standard reference on matrix calculus and look up Hessians. What this is this is basically just a matrix of second derivatives. And the way to interpret this update rule here, which again, I don't want to get into too much because it doesn't really matter for deep learning, but I want to at least put it up here, is what this update actually does is this update approximates the function f using what's called its second order Taylor expansion. So this approximates it using essentially as a quadratic function that involves the Hessian and the gradient of that function. So it involves a second order Taylor expansion, which essentially is this approximation of the function f. And then for this second order approximation, it solves this sort of exactly the quadratic form of the second order function. All Right, and that's the basic idea of Newton's method. Again, I'm actually not intentionally not being too detailed about sort of covering it here because it's not that relevant. But what I want to highlight here, and I should also finally mention that if you take a step size alpha equals 1, this actually corresponds to what's called a full Newton step. But if you take alpha less than 1, this is what's called a damped Newton step. The point I actually want to make is this slide here, which is to say the following. It turns out that the direction for a quadratic function, remember this function that we have on our previous slide, this is a quadratic function. It has just a quadratic term and a linear term. So we had 2 slides ago, right? It had a quadratic term here and a linear term. For quadratic functions, Newton's method actually gives an exact solution to our Newton's method with alpha equals 1 will actually get to the solution in the exact right way. So what you see here is the steps that we're sort of following point exactly to the optimum. So like at each point, we're sort of heading directly toward the optimum. And in fact, if we took a step size alpha equals 1, I'm showing alpha equals 5 here. So we start here and take like, half the way to the optimum, then the next half, etc. But if we took an alpha equals 1 step, we would go right to the optimum here. And this, it's not very hard to prove this. You just sort of, what ends up happening is that the update for the quadratic approximation of f for a quadratic function actually is just the function f, and Newton's method just solves that exactly. Maybe I'll write that out briefly. So if our just in the case of a quadratic, right? So if f theta is equal to 1/2 theta transpose p theta plus q transpose theta, then we can actually solve then the gradient with respect to theta of f theta is equal to, in this case, actually p theta plus q. And we can actually solve this exactly because we can just set, this just means that theta star is equal to p inverse q, negative p inverse q. And actually, it turns out that this term p here is exactly the Hessian that we have, and q is exactly the gradient, or rather, this update when terms cancel give this exact expression here, and you should just get your next expression actually equals this. You can verify this; it's actually quite easy to show. This is the gradient here, but when you multiply the gradient by the Hessian, which is in this case p, then form a Newton update, terms cancel out, and so you get this exact solution here. Right, you can do that as an exercise if you want to. The point is that Newton's method will solve this quadratic exactly will solve this function exactly for a quadratic. And what that means, though, in our, really the important point I want to emphasize in terms of our sort of discussion here, is what this means is that, in some sense, Newton's method is finding the right direction of descent for this function, right? So it's always going directly towards our optimum. And that contrasts with gradient descent, which was sort of bouncing around this function, right? It was not finding, the gradient descent was not finding the actual kind of right corrected direction to the optimum, whereas Newton's method does. Okay? However, and this is why I was sort of intentionally brief about some of these things and not going through a long sort of lecture on Newton's method, this approach is not all that common in deep learning. And I know I'm going to get a few sort of objections here, and people say, well, okay, not exact Newton's method, but approximate Newton's methods are really popular in deep learning. We have all these great methods. We see all these papers about how second order optimization is great for deep learning. And my response to that is I am very skeptical of second order methods for deep learning, at least anything beyond sort of, or I guess anything beyond adaptive gradient methods, which you might argue are second order in some way, but which we'll cover in a second. The high level point here is the reason why this method is so hard to apply for deep learning is that we can't, using sort of, for deep networks, right? Think about how big this matrix here would be. It's a n by n matrix, which is a, right, so this matrix here would be, of course, because it's the number of rows by the number of columns, then this is an n by n matrix here. The number of parameters by the number of parameters. It's n by n matrix. And so in deep learning, it's not uncommon to have millions of parameters, right? Billions of parameters. Some models even have trillions of parameters. And this is just completely impractical to even form this Hessian, right? We're talking about a matrix that's, has more storage than you can ever fit on like a trillion by trillion matrix, right? You can't even talk about that. You also now there and so actually computing the Hessian, let alone inverting it, is completely impractical. You can't even multiply, and the goal we want to do is in some sense here is we want to multiply our vector with the inverse of the Hessian. You can't do that either. Now you can actually implement a product with the Hessian itself. So I can actually multiply a vector not with the inverse of the Hessian, but using automatic differentiation. This is just sort of an aside. This is not something we're going to do here. But it turns out you can, using automatic differentiation, multiply vectors, arbitrary vectors, with the Hessian. So if I have some vector v, I could form this product. But now if I want to form an inverse of the Hessian, I need to do approximate inversion using what are called indirect methods that use just products with the matrix we're trying to invert. It's all doable, but I've never seen a truly compelling example unless you sort of know a lot of structure about your matrix. And this will be a debate. People will disagree with me on this, and I'm sure people will some people might have examples where Newton's method or approximate methods do work. They're also harder to make stochastic, so you have to make these stochastic too. It's just all in all a real pain. And the last point I would say is that while Newton's method in some sense for a lot of convex optimization problems is the right algorithm, for non-convex optimization, which is what we deal with in deep learning, it's unclear that you even really want the Newton direction. It's unclear that this sort of second-order information gives you all that much. And so for all these reasons, we're actually going to very quickly move away from actual Newton's method. But what we're going to do with the rest of this section is talk about alternative approaches that start to still get at maybe accounting for the deficiencies of gradient descent, this tendency to bounce around too much or go in bad directions, that can account for that without sort of going all the way to Newton's method or these second order terms or these second order approaches. You could make the argument that some of these approaches, that some of the methods we're going to talk about even approach things that are called quasi-Newton methods, which are sort of the things that live in between Newton's method and gradient descent. But I'm actually just going to avoid that discussion entirely and just say that we're not going to consider true Newton-esque methods. We're just going to consider kind of additions to gradient descent that try to solve some of the same problems that Newton method gets after without anything like the computational costs of this, but just the same computational costs as gradient descent. All right, so let me now talk about the first one of these, which is very common in deep learning, which is momentum. So essentially, as I said, momentum in some sense is you can think of it like trying to get at a middle ground between gradient descent and Newton's method, but really it's much closer to gradient descent because it's purely a first order method. It only uses gradient terms and has the same complexity as gradient descent. So the idea of momentum updates is that in addition to our parameters, so we're going to have our parameters there, we're also, though, going to carry around a copy of what we're calling momentum terms. Right? And these momentum terms are going to be additional terms that are sort of going to help us make better updates than just the gradients themselves. And the idea of momentum, and I'm going to go again a few slides back for this, the idea of momentum is that when we had gradient descent, and running with a sort of a reasonably large step size here, we kind of bounced around a lot, right? So our first gradient pointed this way, our second gradient pointed back the other way or back a different way. Then our third gradient actually was very similar in direction to our first gradient, right? It's just sort of, kind of repeating ourselves. And in some sense, if you sort of take into account the behavior of this thing over multiple iterations, you sort of get some sense that, what we really should be doing is kind of averaging between these two directions, this direction here and this direction here, in order to find a better update. And that's kind of exactly what momentum does. So momentum forms this other second vector u, which is in some sense a kind of averaging, I mean, not in some sense, it actually is exactly an averaging of kind of the gradients you've seen before, such that you can take steps in this direction instead. And now the thing I should actually mention before I start is there are many forms people write momentum in. So it might be if you've seen momentum before, or if you actually look it up in a package, it might be written in a different way. But I like this way of writing it because it kind of emphasizes the fact that we're averaging between parameters, and it keeps also momentum at a similar scale to the gradient. So Here's how we write momentum. We say that u t plus 1, which is going to be our momentum term, is equal to some multiple beta times our previous, not mu, times our previous momentum term. All right, so it's going to be some sort of, where beta here is some scalar value that's typically, not always actually, but typically less than 1. There actually are some crazy schemes of like larger than 1 momentum, but this is not what we're doing here. So we're going to sort of scale down. So it's positive, but it's a term where we scale down. I guess it could be equal to 0, and then we're just doing gradient descent. But scale down our previous momentum term, and then we're going to add kind of the other portion, 1 minus beta, to be our gradient. Okay, so that's going to be our update for a momentum term. So what the momentum term does is it computes what's called an exponential moving average of our gradients, okay, as we go. Because we sort of, it ends up being sort of essentially a geometric series of the past gradients that we've seen. Okay, maybe I'll write this down. Actually, this was later, but and then what we're going to do is we're going to take our update not in terms of our gradient, but we're going to make our update in terms of the this momentum parameter. So it's going to be u t plus 1. Right, and that's our update for momentum. It's also called Polyak momentum and has a bunch of other names that have been discovered many times, called the heavy ball method, stuff like this. It's has many different names, but it's called momentum typically. Now, this is often written in other forms too. So people often write it as, beta here, but there's no beta on the scaling, or maybe you add alpha on the scaling there. You have to just, if you're encountering the implementation of momentum, you have to just look it up to see what it's doing. But this is the way I'm going to write it. And the reason why I like doing it this way is it sort of keeps u here at a similar scale to our gradients, right? So because it's an exponential moving average of our gradient, it keeps the same scale. Now, to see this, just to sort of write it out explicitly for this one case, I'm not going to do this after this, but what we can do now is we can kind of look at what this sort of momentum really would be here, right? So if we look at sort of what is ut plus 1, well, that would be equal to, I'm going to write sort of in the other order now, it would be sort of equal to 1 minus beta times the gradient of our current term, plus beta times ut. But let's also expand ut out, right? So ut equals plus beta times ut, and ut equals, beta ut minus 1 plus this term. So this would then be beta times 1 minus beta of the gradient at the previous time, f of theta t minus 1, right? Plus it would be again then beta squared plus, I guess, beta squared times ut minus 1. But we can expand that to 2 to make that, say, equal to 1 minus beta times the gradient at times t minus 2, etc. Right? So what we're computing in some sense here is we're computing kind of a geometric sum, because we have these beta terms, we have a beta term there, we'll have a beta cube term, etc. So a geometric sum of all of our past gradients we've seen. Okay, and that's sort of what we're doing here is we're computing kind of again, what's called an exponential moving average, so sort of a weighted average of not just our current gradient, but all our past gradients. And that's what a momentum term is. And because of this, it's sort of able to capture better what our actual, which direction we actually want to move in. It sort of averages out our past gradients in a way that lets us move in a better direction. All right, so this is sort of the basic approach. And what you see here is that on the left here, I am showing our old gradient descent method, which kind of balances back and forth. So this is actually, hopefully should be apparent that if you pick beta equals 0, then this would just be equal, then this term would just be equal to the gradient. So beta equals 0 sort of is just gradient descent. Beta equals 1 doesn't do anything because there's you never factor in the gradient. So beta has to be less than 1. Again, typically, there are crazy methods that actually have beta greater than 1, and these don't make any sense, but sometimes people can use these with the right weighting. You typically have to have a different, you can't do this update exactly with beta greater than 1, but you can do sort of modified updates sometimes. the point being that beta equals 0 obviously is gradient descent, and you things, gradient descent here just bounces around like we saw before. But if we pick beta equals 0.7, what we see is we sort of, instead of this, we kind of smoothly start averaging these things and eventually kind of converge. So that's sort of the idea there. Now, you may sort of notice that we actually, because we have a bunch of things, we're kind of, some history kind of our momentum built up. We often overshoot the optimum and things like that. But these are just sort of effects. Momentum is just a very common approach in practice. All right. Now, one thing you might notice about momentum is that there is sort of an interesting effect here, which is that at earlier iterations, UT is smaller than the gradient, right? Because, for example, what's common to do is to initialize the momentum term, say at 0. So you'd have something like U0 equals just 0, right? And then you'd have U1 equals, well, beta U0, but that's just 0, so that term doesn't play into account, times 1 minus beta times the gradient of f, its initial parameter. Right? Wherever, again, we'll talk about initialization in a second, but this theta 0 is just however you initialize theta. And what you notice here is that this is a lower value than, this is sort of, essentially a scaling on the gradient that makes this first gradient step smaller in value, right? So this sort of, if you remember the previous slide here, the first gradient step kind of takes a step like that, but the first momentum step takes only a little step because it's kind of warming up. The gradient's still kind of getting, the momentum term's kind of warming up. All right? So what's common to do, and this is sometimes called sort of a biased momentum, or a biased momentum term. So it's an expectation, it's actually smaller in magnitude than the gradient is, which sometimes you don't want. You might want to sort of rescale it. And it turns out we can correct this if you want to correct it. And the idea would be we just replace our update as that we had before. So our update before was theta t minus alpha times our momentum term. What we just do is we divide this momentum term by a scaling factor that sort of corresponds to how far along we are in our optimization. Because this sort of biasing you see here, this will decrease the longer we go, right? The more kind of past history we have, the closer and closer our momentum gets to the same scale as our gradient. And so the correct factor essentially to do, and you can check this is sort of the right factor to do, is you divide this, maybe I'll write it up like this. You divide this term by 1 minus beta to the t plus 1. So for example, when you have U1 here, actually this might be just beta t. It depends on your notation here. Oh no, because this is UT plus 1, right? So this would be at iteration 0 essentially. You would be dividing it by beta, etc. So this term here I want to emphasize. So this term kind of corrects the scaling, and basically for U1, what this would do is this would divide this term here by 1 minus beta, and so that would cancel out, and so we would actually have the first gradient. The thing I want to emphasize here is that this notation here, this actually is not a subscript, this is a superscript, and it is actually a exponentiation. So I am taking b to the power of t plus 1, and that actually is the correct term to scale our momentum by in order to cancel out kind of the expected downsizing you have due to initial iterations. And what we see here is we run this, you kind of get what you would expect, right? So our first term here is, in fact, our normal gradient step, actually. So this term actually looks exactly the same as our first one because we've rescaled our term to be that first step. And then subsequent terms kind of are similarly corrected. So you aren't taking small steps, you're taking actually just kind of larger steps here. And what we find is that actually this does typically converge faster. So just like, and I think I didn't mention it, but just like momentum converges faster than gradient descent, this converges a little bit faster. Sometimes you want to do this, sometimes you don't, but if you do want to unbias your terms that sort of take similarly sized steps at all iterations, you can do that. It actually is not always a great idea. I mean, sometimes maybe you want to take smaller steps at first because you don't have a good estimate of the right direction. So maybe you want to take smaller steps. It's really kind of up to choice. One more type of momentum, which I just want to add here because it is sometimes used in deep learning, is Nesterov momentum, which actually, for various reasons, is a very useful sort of tool, both actually in practice in some cases, but also it's a very nice theoretical tool. So I should admit now that there are a ton, and I can never cover all of them, but there are a ton of tricks that people use to accelerate gradient descent and things like this to sort of make gradient descent converge faster. We are not going to go over all of them at all. We're going to go over the sort of the most common ones for deep learning, momentum being one of them. But another common one is Nesterov momentum. So what Nesterov momentum does is it actually takes our normal kind of momentum update and makes a minor tweak to it, which winds up being a fairly good idea. So what it does is it takes our kind of our normal momentum update. So that would be 1 minus beta times the gradient of f theta t. But instead of actually just doing the gradient at a current point, we actually kind of take the step that we would take based upon our current momentum term, evaluate the gradient there, and then update based upon that term. All right, so that seems kind of odd, I know, but and I actually don't want to get in, and then so our gradient update is the same then. So it's the t minus alpha u t minus 1. And you can do, of course, bias correction for all these things too. That also works. Now this seems like kind of an odd thing. It's not quite clear why this is the right thing to do, but without going into this at all, what I will say is that for certain convex optimization problems, it turns out this is actually a very good idea. For sort of somewhat technical reasons, you can get better convergence. You can prove better convergence rates for this kind of updates than you can for normal gradient descent. And so this is sort of a good thing. I mentioned that here not because it's actually we don't really care about the convergence properties. Again, just like with Newton's method, how much those really extend to non-convex optimization we deal with in deep learning is somewhat unclear. But this is a nice trick to sort of know about, that you can compute kind of gradients at kind of look-ahead points in some sense, and that often is a good idea. Okay, so that's the basic idea of Nesterov momentum, and it can be implemented in a few different ways. There are a few different variants of it that have slightly different takes, but that's sort of the core idea of Nesterov momentum, is that you're sort of evaluating your gradients at not quite at the current iterate, but at some updated point, some sort of like semi-small updated point before you form your final update. Okay, and in this case, actually, it converges quite a bit sort of more smoothly, right? So you sort of get that nice kind of convergence pattern, and it does, in fact, to sort of converge faster for the same kind of values of your subtleties and momentum. It kind of has a smoother trajectory and it converges nicely. All right, so the last element I will talk about, and I guess the last element I'll talk about before we talk about stochastic methods, or just mention stochastic methods, is about Atom. So Atom probably, if you look kind of at the history of a lot of deep learning, there's the sort of different optimization methods have come and gone. They've become trendy and untrendy for a while. I have to give it to Atom. It really has preserved as one of these methods that kind of everyone tries. I'll talk about this also in a second, but it's possible this is just sort of for historical reasons. Maybe the world could have evolved very differently, but we're at a point, at least right now, where Atom is probably one of, Atom and just kind of pure SGD with momentum are probably the two optimizers you really need to know about in practice in deep learning, and then you can try other ones if you want to. So it has really been an extremely successful algorithm. There are a lot of very similar algorithms, I should mention, that are just slight variants of it, and so there's many ways you can do similar things, but this one has preserved for whatever reason. So the idea of Atom, which belongs to a class of methods called adaptive gradient methods, and there are other adaptive gradient methods, but again, it's a fairly successful one, is that one sort of fundamental problem with gradient descent is that the scale of the parameters that you care about can vary, right? Both the scale of the parameters and the scale of the gradients can vary over optimization, right? So, I mean, if you just, again, look at even these simple examples here, right? The objective changes differently in different dimensions, right? So it's sort of more stretched out along, it's more stretched out along this dimension, say, even just on the actual dimensions themselves. Obviously, it's sort of actually stretched out along this dimension, but even just considering theta 1, it's sort of more elongated along this dimension than it is along this dimension. Right, and we want to somehow account for these things when we talk about these gradient descent. You want somehow, it would be nice if you could, in some sense, kind of account for the different scales of the gradients, so as to update your gradients or update your parameters in a uniform way, kind of regardless of the scale of their gradients. Right, and this is the idea of adaptive gradient methods. And what Atom does is it just uses momentum, actually 2 momentum terms. So it's going to use, rather than just 1 momentum term, that'll actually be the same as our previous approach. But instead of 1 momentum, it's going to use 2. 1 momentum term to capture sort of the magnitude of, or to track the gradient itself, and another magnitude term to track the square of the gradient, which captures in some sense kind of the magnitude of the gradient. And then we're going to normalize by these respective things. So let me make that sort of explicit now. So what the UT in Atom is just a normal gradient term. It's just going to be our gradient. I'm going to say beta 1 here because there's actually going to be 2 different momentum parameters. It's going to be our same momentum update as we had before. So beta times 1 plus 1 minus beta of theta, or our gradient at theta t. Okay. And that's our first update. What our second update will do is it wants to estimate, in some sense, what is the magnitude of the average, and the average magnitude of this gradient of this gradient vector in some sense. And it's going to do this element-wise. So it's not like measuring like its norm or anything. It's measuring what is the magnitude of the average magnitude of some sense, each individual element in our gradient vector or gradient tensor or whatever. And the way it's going to do that is it's going to have another momentum term, which we're going to have, where we have a different, and we're going to have different momentum constants on each of these 2 terms. But B2 times V2, BT plus 1 minus B2 times, and now we're going to take the same gradient term, theta t, but we're going to square it. And this in particular, I want to emphasize, this is element-wise squaring. Can't write today. Element-wise squaring. Okay. So what this does is this computes a running average of the square of the gradients. And what this kind of corresponds to is, in some sense, assuming the gradient is 0 mean, for example, so you're sort of bouncing around the point you want to be at. This is going to estimate essentially the variance, or more generally, kind of the second moment of the gradients. Okay, and now what we're going to do is we're going to scale our gradients, or really, in some sense, our momentum terms, so our U terms, by their respective magnitudes as captured by the V terms. And so in other words, the final update for Atom says that theta t plus 1 equals theta t minus our step size alpha times ut plus 1 divided by the sort of normalized magnitude. And the way you do that is you would take the sort of square root of vt plus 1. And because we don't want to, if that happens to be 0, we don't want to divide by 0, so we'll add an epsilon. You could add the epsilon inside the square root or not, but the convention is to not add it inside the square root. And the other thing I want to emphasize here too is that these operations are all being done element-wise too. So this is element-wise. So again, these things here are both vectors that are the same size as our gradient. So this is all sort of operations. So these here are all operations on vectors, and they're all element-wise operations. So both the division and the square root are all done also element-wise. All right, so what we're doing is we're taking each component of our gradient, or really of our momentum term, and we're scaling it by its magnitude. Its sort of average magnitude, really the square root of its average squared values, right? And so what that does is that puts all the gradient terms in a similar onto a similar scale. And this approach in practice sometimes works very well, right? So sometimes making them all the same scale, sort of avoiding big differences in scale over the gradients, is a very good idea. And it helps us to sort of get better convergence of our algorithm. And we can see that sometimes. So again, this is, Atom is not a great, well, it is not often the best method for sort of pure quadratic functions, or rather, yes, it's not, it doesn't, again, we're sort of reaching the limits of what we can learn from quadratic functions here. But what you do see actually is that Atom very nicely, after the first step, sort of accounts for the relative scales of the gradients very well, and proceeds in this very nice sort of direction that looks actually a lot like the Newton direction. And you have pretty nice convergence here. Maybe you could get it even a bit faster by increasing the step size and things like that. All right, so this is Atom, and actually that's going to be the end of the algorithms, of the sort of the specific optimization methods we're going to talk about, because it kind of covers, at least algorithmically, what are the main approaches. Now, I haven't talked about. I'm going to talk in a second about the fact that we're doing all these actually in the stochastic setting, not in the batch setting. But these are sort of the standard algorithms that we're going to use. Again, as I said, sort of Atom seems to work pretty well in a lot of cases. It and just sort of plain SGD, I would argue at this point, are kind of the two optimizers you really need to know about. And after you want to, after you want to, if you want to sort of try out other things, you certainly can. And this is in some sense arbitrary. I really should mention. So I like to think that there are alternate universes where a different algorithm was published in 2014 and kind of became the dominant algorithm for optimizers. Like maybe we'd use the absolute magnitude of the gradients instead of their squared value with the square root, right? Maybe you would use Nesterov acceleration in it by default. Maybe they wouldn't unbias it. Oh, I should mention too that if you see the updates for Atom, you typically see more than just this, and that's because they are doing this unbiasing of momentum. So that actually is quite important here, because these terms, if they're too small, won't always make sense. And so that unbiasing, which essentially divides, which takes this term, I'll only write it briefly here, but takes, for example, this term and would divide by 1 minus beta 1 to the t plus 1. You will typically see that term included in the definitions of Atom, but that's all it is. It's just applying that unbiasing to the updates. Okay, so you actually in your homework will implement the unbiased version of Atom, because it is the standard. If you see the equations of Atom written out, that's just what those things are doing. But this is the idea of Atom. But there are other universes where maybe like they didn't do unbiasing, right? Because actually it's actually okay not to do unbiasing, because the two terms u and v are biased in the same way, and you're dividing one by the other. So, or rather, one's you're taking the square root of one, so you have to sort of do it in different ways. But there are all these sort of different universes where slightly different variants of these things became dominant instead of Atom. But we are where we are, and Atom is well tuned and hard to uniformly beat. I know there are constantly new optimizers that come out that people in their paper show just completely reliably that this thing beats Atom in all cases, and yet for some reason they never really become dominant as sort of the go-to default. And I think that if they really worked better across all those cases, they probably would become the default. Maybe not. Maybe people are just so set in their ways that doesn't happen. But just we sort of are where we are in this world. Even if other universes are possible, this is where we are. All right. So the thing I want to sort of end on here in the optimization section is that actually we don't use any of the algorithms like I showed you before. So I think at this point we sort of reached the, and the figures I was showing you before, with the convergence and all that kind of stuff, we've honestly reached the limit of how much you can get intuition from just like looking at these optimizers on a simple quadratic convex problem. Because the reality is we don't implement sort of gradient descent like you saw there, or any algorithms like you saw there. What we actually do is implement stochastic variants of all of them. We talked about this before, but the core idea, of course, is that the optimization problem we actually care about, it's not just any optimization problem, it is an optimization problem that involves a sum or an average of many losses over many different examples. And so to get an approximate an approximation to these descent directions, we can often just use a very small number of these examples called a mini batch, right? It actually can be as small as one. You often use more for numerical reasons, but you can get sort of good descent directions by taking a smaller batch of these things. And so what we really do in practice is not the sort sort of single step update you saw before, where we sort of take a gradient over everything. But what we actually do here is we actually set our updates to be theta t plus 1 equals theta t minus, for some subset of our examples b, we sum instead over just the examples in our subset b and take their gradients, right? So this is, every time, and to be clear here, when I write gradients or when I write this update, you would just do the equivalent thing for momentum or for atom or for whatever else. Those all involve gradients, and this is just the gradient that you use now instead. So you have your hypothesis h theta xi and yi. Now you take it to sort of normalize properly. So before we would normalize by the sort of number of examples, because that's our average, and take us up as alpha. But so here we have to normalize by the size of b, right? And that becomes our new update. And that actually is the update. And as I said, all our other algorithms work in the same way. If you just replace, whenever you see the gradient, you don't use the gradient of the whole function. You use this term as your gradient. The one exception is Newton's method, where you have to come up with an analog of the second order derivative for this thing too, which is actually not that easy. It really is a pain. So it's again why we often don't use second order methods. But whenever, for first order methods that just use the gradient, you just replace your gradient term with this term here. And the difference here, I mean, again, the idea, as we talked about last time, we talked about this before a little bit, but again, the idea is that, you're taking many smaller steps in the approximate direction of your objective, even though each one is noisy. And we can even view this in our old example. It's an imperfect example here because our old sample was not actually a sum of multiple losses. It was just a single quadratic function, though you could come up with a sum that leads to that quadratic function, sort of neither here nor there. But if we sort of take if you think about like approximating this thing, what SGD is really doing is it's taking sort of multiple smaller, noisier steps. And often you'll find that, even if gradient descent is sort of seems to be sort of a more precise algorithm sometimes, if you do SGD in other settings, what you're doing, instead of taking these like single, maybe bigger steps in the exact gradient direction and still bouncing around a lot, what SGD does is it takes many more cheaper, kind of smaller steps in noisy directions, which you can kind of, bounce all around. But the point is that, there are many cases where this iteration could be many, infinitely so, if you have infinite data, faster than actually computing a full batch gradient step. So there are cases like where after the same number of actual work done, with gradient descent, you would be, have taken one update, and so you'd be here on your curve. Whereas with SGD, you'd be going all the way to your final update. In other words, you'd be here on your curve. If, say, one iteration was 30 times more complex or cheaper than in the other setting. Right, so this can be a really, really stark difference sometimes, where it's extremely beneficial to take many small, noisy steps over waiting to take one big, correct step, which isn't even that correct because gradient descent's not even that correct for the objective we care about, right? And sometimes you even want noise because noise can even help you get out of, escape sort of nasty regions in the loss function and stuff like this. And so this is really what everyone actually uses are these stochastic variants. And so whenever you see a gradient, don't take the actual gradient, take this thing here. All right, so again, important takeaways. All methods we use that you saw before, you will actually use them in their stochastic form, not in their sort of full batch form. And the last thing I'll say is that we have reached, while I think those plots of showing these functions operating on, simple quadratic functions are very instructive, we also probably have reached the limit of what you can really learn from that, because deep networks are not convex quadratics. If they were, we would be in a very different spot, optimization-wise and probably, machine learning-wise. They are very non-convex, very non-quadratic, very weird functions that we don't even fully understand, to be honest. And so the reality is, to really understand how these methods operate on deep networks in practice, you just need to experiment and get an intuition of how they actually work on different deep network types. Okay, and with that, I just want to start the final section of this lecture, which is going to be actually just a brief introduction to initialization in optimization. TQ is going to cover this a little bit more in some of the next lectures also when it comes to implementing deep networks, but I want to mention it here because when we talk about optimization, it really is a key point that ties into optimization, and so it's worth emphasizing this here. Okay, so one of the key questions that we will have when optimizing a network actually is, what do you choose for your initial values of Wi and Bi? Right, so those are our parameters in the network. And in the previous example, I just started theta like at some point, right? I just started theta. Oh, theta is this value. But that, doesn't really tell us anything, right? How do we pick those initial values for our parameters in a real neural network? How do we predict our initial values for those parameters? What you may have seen in optimization is, in convex optimization, a very common thing to do is just initialize your parameters to 0, right? So if you have softmax regression, for example, you can initialize theta to be 0, and that's completely fine. It's sort of a nice, easy value to initialize to. It's maybe not going to be too big or something like that. It'll also, there's no randomness involved, stuff like this, and so it's very nice. But unfortunately, initializing your parameters to 0, which is sort of standard in convex optimization, does not work for deep networks. And so why is this the case? Well, let's think about what happens if we initialize our parameters to be 0. Well, what we would get is we would get the fact that if we take sort of if we just think about our sort of iterations of our network and take our iterations of our network as just iterates, right? So we would just take like our, even without our bias term for now, because it's a bit simpler, adding a bias does not fix this problem, to be very clear. If adding a non-zero bias still does not fix this problem. But also we can think of this as just sort of, if we initialize both our weights and biases to 0. So what would our sort of forward pass be? So our forward pass would be zi plus 1 equals sigma I zi wi, which is going to be, because wi is 0, this is also just going to be 0. Right? Always. We also have the case that the GIs would be GI plus 1, Hadamard with I C I WI WI transpose. And so those after the first iteration for any sort of because we're multiplying here with WI, this would also equal 0. And unfortunately, what this means is that all your gradients are also 0. And so if you initialize your parameters to be 0, you have more than one layer in your network, your gradients will also be 0. And this is very bad, right? Because this means that none of, really, other than the last layer, actually in the last layer there'll be 2, because in the last layer your x's are 0, also your sort of inputs are also 0, because your z's are 0. So all your gradients will be 0, and you will not be able to learn very much, right? You will just, gradients are all 0, you will not update your parameters. And so what this sort of means, in other words, another way of putting this is that we've sort of heard this notion before that neural networks have many local optimum. And this is not quite, I mean, I should be precise here. It's actually, technically speaking, these zeros are a saddle point, not an optimum. But basically they mean, roughly speaking, this point, the point where all the parameters are 0, is actually sort of a fixed point of the gradient update. It's a point where the gradients don't make any changes, which, we think of those often as like local optima, or, I guess local saddle points and things like this. But it's a really bad one, right? Because predicting all zeros is probably not a very good model. And if you initialize to be all zeros, you will never move from there. So this is a really bad thing to do, and you don't want to initialize your parameters to be all zeros, unlike in convex optimization. So the question is, what do we do instead? How do we initialize parameters instead? So let's just initialize them randomly. That's a good choice, right? If there's nothing else to do, let's just pick them randomly. For example, let's pick let's imagine we just pick our parameters to be normally distributed with mean 0 and some covariance some variance sigma squared. So when I write it like this, what I mean is that each sigma squared I, what that means is that each individual element of our weights are sampled. It's a little bit of abuse notation here because technically this could be a tensor and this is a matrix, but whatever. All this means here is that each element in our entire weight matrix or weight tensor or whatever is sampled according to an independent Gaussian with variance sigma squared. Now, the key point here is that this you can do this, and this is actually what typically does happen, or variants of this are typically how networks are initialized, just again with random numbers. Either it doesn't have to be normal, it can be uniform, stuff like that too. But you'll implement some of these in your homeworks. But what's important to emphasize here is that the choice of our variance now is not just something where you can choose a lot of different parameters and they'll all work. The choice of the variance has huge implications for the resulting performance and weights and everything, and magnitudes of the gradients and everything else for your network. So to illustrate this, I'm going to actually take an illustration on MNIST with 50 layers and relative nonlinearities. And I'm going to plot, and this plot here, what I'm plotting is I'm plotting the norm of the activations. That's like the norm of the ZI terms as we progress through the layers of this network. So this term here would be the first layer. This term here would be the 50th layer. And I'm showing this for 3 different values of our variance. So for 1 over n, for 2 over n, and for 3 over n. And what we find is that this choice of variance leads to very different performance for our or very different sort of behavior of our networks. What happens in the case of sigma squared equals 2 over n is that the norms stay roughly the same throughout all the iterations, and the gradients are all at sort of magnitude 1. On the other hand, for 3 over n, the norms increase as we go, and the gradients get very large. And for 1 over n, so again, these are just, within a constant factor of each other. They aren't that different. I'm dividing the same by n. I mean, if you just pick a random number, who knows where it would be, right? For 1 over n, they go down. So there's a few like weird things happening here, right? This seems kind of odd. And the few sort of key points I want to make. So the few points of the choice of initialization matters. How this work really matters. But the other key point of initialization, and so I guess the thing I want to highlight here is that this is very different, again, from our intuitions that we may have in sort of traditional convex optimization, say, where initializations often don't matter that much. I mean, to a first approximation, maybe they don't matter that much. Here, it really matters. So initialization, 0 just doesn't work at all, but random sort of only works when you have the right variance. The other thing that I want to sort of mention, I'll come back to this actually in a later lecture as well, is that weights don't actually move that much in deep learning. So we have this notion, right, that, it doesn't matter where you start, or at least I, for a long time, had this notion that, with optimization, it doesn't really matter where you start because, eventually all points will converge to the same optimum. And maybe with neural networks, it's not quite the same optimum, but maybe it's, a few optimum you converge to or things like that, right? And that is really, really untrue. So sort of take the reality is, when you actually look at how much weights change over the course of optimization, the differences in initialization can far outweigh the differences you actually see in optimization. So weights, the way I'll put it briefly, and again, we'll come back to this later, so I won't belabor this point too much, but weights don't change that much. Of course, they change somewhat because they make the network loss small, but the initial value of the weights, they stay relatively close to it, and in sort of in some other sense. And this is very important sort of for gathering intuition about what optimization is really doing in deep networks. But we'll move to that come back to that actually in a later lecture when we talk about normalization of these things. Okay, so then the last thing I'll sort of mention is I'll look at this effect we saw this previous time and try to explain what's happening here. So why is 2 over n the right variance to have in this case, and how does this maybe motivate how we should initialize weights? So the idea is that because when we think of weights initialized randomly, then it turns out we can actually think of sort of the product, or think of the intermediate terms in a network in loose terms, because this is not quite exactly correct. But we can think of them roughly as sort of random variables that have means and variances themselves. And we can actually show a lot about what's going to happen to these things by the central limit theorem, right? So central limit theorem says the average value of the sum of, or I guess the expectation, sorry, I should be precise here. It says that if you take a bunch of random variables, kind of any distribution, and average them all together, that average, as treated as a new random variable, over multiple draws of the original variables, approaches the Gaussian, if you have the proper scaling and things like this. So and under lots of conditions that I won't I won't get into. So what we can do in some sense is we can sort of be sort of a bit more than a bit, but this can all be formalized actually, but we're going to be very, very informal here. And think of like all our intermediate aspects of our network as being kind of normal random variables, and we sort of want to see what happens here. So first of all, let's think of our inputs to a layer. This is holding for x right now, but this would hold for later layers too, as being normal with mean 0 and variance 1. And let's think of our weights as being normal with mean 0 and variance 1 over n. All right, so this is sort of the 1 over n case, not the 2 over n case, but we'll come back to that in a second. So if this is the case, then the expectation of the product of these two things, well, they're going to be independent random variables here. Obviously, our weights are independent from our examples. Again, assume this is the case for now. This is like a newly initialized network or something. This is going to be, because the variables are independent, this is going to be equal to the product of their expectations. So x1, or x, actually, yeah, so this is going to be equal to the product of their expectations. Let's see. EWI, which equals 0. And furthermore, because they're also independent, the variance of their sum is going to be equal to the sum of their, the variance of their product is going to be equal to the product of the variances. So this will be equal to variance of xi times the variance of wi, which is going to equal 1 over n. And that's for a single sort of product between xi and wi. But what we have here, what we actually want to compute now is we want to compute, what we're doing in a network is not taking a single sort of inner product between, or a single product between one weight and one dimension of the input. We're actually taking, an inner product of all our weights and all our inputs here, right? So we're taking this inner product here. And so that inner product is, of course, just, this inner product here. My battery must be dying on my pen or something. This inner product here is, of course, just equal to the sum from I equals 1 to n of xi wi. So in other words, it's a sum of, in this case, kind of random variables that we think about it, right? And the expectation of the sum of random variables is equal to the sum of their expectations, right? And the variance of their of the sum is equal to the sum of their variances. And so what we have here is we have the expected value of this inner product of all the weights and x is equal to 0. And because we're adding up n copies of 1 over n variance variables, the variance of the inner product is going to be equal to 1. All right, so what this means here is that if, sort of very informally speaking, so in other words, like, this thing would go to a random variable here. So what this means is that if we have now consider sort of a whole set, not just one, but consider a whole set of n activations here, and we think of wi as being initialized in this way, then our iterations of the whole network, right? So zi here would equal wi transpose times zi. So in other words, this is a whole bunch of inner products of weights that look like this, right? It's a whole bunch of these things that look like that. This whole next layer, if we assume that the first layer is normal with mean zero and covariance I, i.e. it's a bunch of independent random normals, then actually the same is true for this product here, because every element of this matrix vector product is essentially equal to something that looks like this, right? So this whole thing would also be normally distributed with mean zero and covariance I. And this is really the important point here. And this is actually probably, kind of in some ways as deep as the probabilities we're going to get in this course. But the point here is that if you pick this value of the covariance and you have a linear layer, so if you had a linear layer, so a layer with no linearity, then this next linear layer would also have the same, the random variable with the same mean and covariance as our input. In other words, choosing this particular initialization maintains the variance of subsequent layers if this is our update. Now, that's not a very interesting update. That's a linear layer, which is, there's no point in doing that. But that's what it would be. And the key point is that, which I'm going to say sort of very informally, is that, each element here of this is normally distributed between 0 and 1, right? And so we sort of expect half of its values to be negative and half of them to be positive. And so if we use the ReLU nonlinearity, then like half of those elements will be set to 0. And to account for that, to sort of have the same property that we sort of want to maintain variance over layer to layer, we actually need to initialize our weights not with 1 over n variance, but with 2 over n variance. That accounts for the fact that we're setting half of them to 0. This is sometimes called the Chi-Ming normal initialization. And it is sort of one of the standard ways of initializing weights in a network. You will see many others as we implement these things. And in fact, in the next lectures, Tianchi is going to go through kind of how you would set up a library to do these things. But over this and in the next homeworks, you will actually start to implement all these aspects into kind of the different component parts: optimization, initialization, eventually things like layers, normalizations, and linear layers, stuff like this, into what will make up sort of a first iteration of a deep learning neural network library. All right, see you next time.